Hey, how's it going? Thank you for coming back to another edition of OpenPair. My name is Keith Clark, and today we're going to be talking about gradient descent for linear regression. Just so you know, this video is a study session. Just as it's labeled, the purpose of this video is just me walking through a lab for Jupyter lab, or for Jupyter Notebook rather, and I'm going to be showing you how I model out gradient descent and do the optimization for figuring out the lowest cost. And yeah, if you want to just like study with me and follow along, that this is a great video. This is a video for you. So the first thing I'm going to do before we jump into this, I want to just remind you that for this video, there is actually a course that this video is related to. It is the Coursera machine learning course. The link is in the description down below. And if you want to follow along, that's the course you'll want to take. This is lab number 5 from that course. It's not my course, by the way. This is actually a course that's sponsored through Deep Learning AI and Stanford University. It's a great course though. And if you want to follow along as well and do this inside of your own Jupyter Notebook, there is one caveat. This is what you're looking at right now on this screen here. This is actually the official lab that is provided to you by the course. And you see here that there's this file here, lab_utils_uni. This file is not available publicly unless you have this course. If you do, all you have to do is go to the lab here, click lab files here to expand this, open up this folder, and you'll see lab_utils_uni.py. So that's the file you'll need if you want to run this inside of your own environment for your Jupyter Notebook. Otherwise, you can just do this straight through the course. If you cannot find this file in this specific location here, the other place you could find this file is by going to beta version, and you'll find that file in here as well. So it's the same file. I checked, I used that other one in a previous video in this series. So that's just my little caveat before we get started. So I'm going to switch back. This is my environment. I'm going to walk through this lab, and I'm going to show you how I do it, talk through it. This is something I'm learning about as I go in this series. And oh, one more thing. Gradient descent involves a little bit of calculus, just like the smallest little pinch of calculus, because this is dealing with like some math notation and it involves some derivatives. You don't need to know about derivatives in order to understand gradient descent. I will explain it to you, but if you want to know more information about gradient descent, how it works, how the math part of it works, the derivatives and all that, if you go to the description of this video, there is a link to the Coding Train, which is an excellent YouTube channel. And there, Daniel is explaining what a gradient descent is, what it means, how the math works out. He's walking you through on a whiteboard, like all the steps and everything involved with that. So if you want to know more about this topic, like from like a math perspective, I would recommend checking out that channel. So yeah, without further ado, I'm just going to do like a really quick review just to kind of tell you a little bit about what we're doing today. And yeah, let's just go ahead and get started. Okay, so basically, we're doing this in the context of linear regression. And just to kind of back things up just a little bit, let's take a look at what linear regression is. Linear regression is assuming that we have a training set of data that we have modeled out. And for linear regression, what we do is we draw a regression line. And this regression line, the purpose of it is to, as close as possible, represent the data, or at least the trend of the data. A regression line has two major parameters. These two parameters are also called coefficients. And these coefficients are the weight, which is the slope of that regression line, and the bias, which is the y-intercept of the regression line. This is something I explained in the previous videos in this series, so I won't go super into depth with this. But the reason why gradient descent is important is because this line that we generate for linear regression, this line does not inherently do much to help us. In order for this line to serve the purpose, which is to help us make a hopefully accurate or closely accurate prediction, in order for that to work, we need to have the right weight and the the right bias configured, so to speak. So the question is, how do we understand like what the correct values are when we're trying to get the weight and we're trying to get the bias? These are visualizations that help us to do this. Gradient descent is all about understanding like how do we get from the highest error to, or highest cost rather, to the lowest cost. In this 3D visualization, this 3D surface plot visualization, you can see here that the lowest cost is this blue region here. And so when we say gradient descent, we're talking about descending down the gradient of this surface to the lowest point, which is called the minimum. And this gradient descent algorithm is designed to sort of do that for us without us having to manually, change those variables for the weight and the bias. And if you want to know how to make these graphs and stuff, that's something that is facilitated by this file that I mentioned, this lab utils uni file. It has some extra like stuff in it that helps make these visualizations, but essentially this is being done with matplotlib. And these graphs here are kind of just a really convenient way of showing us how closely our linear regression is like able to model the data we have. And the lower the cost, the better the prediction, the more integrity our model has. Okay, so I'm gonna go back to the notes for this, for training with linear, or with the gradient descent. So this is a study session, like I said. I'll be doing like a little bit of explaining as I go. If you want to know more about this topic, like in a more concise, explanatory way, what you'll wanna do is you'll wanna come back for the next video after this one, which I'll do a review to sort of like, seal the deal, make everything make sense, and be a little bit neater, because this will probably be a little messy. I'm just literally walking through this as I do the lab myself. Every time I cover my face, by the way, I lose my little special effect. It's pretty close though, right? Okay. Okay, so let's do this. Okay, so the purpose of this lab right now is to animate the process of optimizing the weight and the bias using gradient descent. Optimizing aims to achieve the lowest cost. Okay, so our problem statement, let me go ahead and change this. I'm gonna try to talk as much as possible, but we'll see how it goes. Let's use this small set of data. These notes and everything will be published. I'm working on a Substack right now where I'll publish all my notes as PDFs where you can get all of them. And I'll post those links as soon as possible. Just go ahead and subscribe to the channel, follow and everything like that. Then I'll let you know in a video when that Substack is like ready to go and when you can get these cheat sheets, these notes, okay? Okay, so okay, so what we're dealing with right now is we're dealing with some assumptions here. The price of a house in thousands of square feet correlates to the, or in thousands of dollars, correlates to the price of the house in thousands of square feet. Okay. And, okay. So that's our first assumption, is that, and this is going to be our training data as well. So I'm going to show the training data here. I'm going to show the training data here using a table, a data table. I'm actually not going to type this out myself. I'm just going to pop it on in here. Oh, I forgot my little dollar symbols. I think I need 2 backslashes for that to work. Yeah, there we go. Okay, so I'm gonna put this here like that. Can I highlight? Does highlight work in Jupyter Notebook? Nope, it doesn't. Okay, I guess that is not a Jupyter Notebook thing. Oh well. Okay, so that's our data table here. We're going to start off with just two rows of data. So this first, or this 0th index, this is a house that is 1,000 square feet and the price is $300,000. The first index, the second house, is 2,000 square feet and its price is $500,000. This is the same data set I used in the previous videos for this. Okay, so like last time, the first thing we need to do is load the data set into variables. By the way, I would just say, like, if you're doing these types of like labs and stuff, it's good to do all of this manually. I know the courses will say like, oh, just run these different modules and everything, but I never do it like that. I always do everything as much as possible. At least the code part, I do by hand. Some of the like little notes and stuff, I might copy and paste if it's just easier. But I try to at the very least, get them from my notes. And I like to do all of the coding part by hand, because even though you can do this by copying and pasting and just running, and you might even be able to achieve some understanding, I personally find that it's just much better. I get like a more intuitive understanding of what's going on, or implicit understanding of what's going on. And I think that'll get you a lot further. So yes, please, please, please don't just copy and paste. You're missing out on most of the learning when you do that, in my opinion. Okay, so we're setting up arrays using NumPy for the X training data and the Y training data. And we're treating these as floats. These X's are our inputs, these Y's are our targets. Okay. So the next thing we need to do is we need to calculate the cost to compute. We're gonna make this into a markdown just to make some notes here. Another thing too is when I do my notes in this, I'm not just sticking to the comments and stuff that are done or provided by the course. I'm like putting things in my own words as well, which is going to force me to better understand exactly what's going on. I guess the theme I'm saying is like, get as far away from copying and pasting as possible. And you're going to make more mistakes that way. You definitely will. You definitely will find more mistakes and have a lot more errors and things will break. But you want that to happen. You want to have as messy an experience as possible, because you're going to have the optimal opportunity to learn. And that's really the point of all this. So yeah, put everything in your words, make your mistakes, mess it up, and make sense of it. Like, that's the actual work of learning. Okay, so we're going to compute the cost. And compute the cost means that we're creating a function that will iterate over the training data and provide us a value that is representative of the squared error cost function. I think I put the hyphen in the wrong place. So we're getting a number that is representative of the squared error cost function. And I'm gonna go ahead and make that bold. Okay. Okay, so let's do this. Cost. So find compute cost. we have 4 arguments, x, y, w, b. X is our input, y is our target, w is the weight, and b is the bias. Remember, m is the size of our data array for the features. So to get that, there's a method in NumPy called shape. And then we're going to start the cost at 0. We're creating basically a variable that's going to hold this cost, and we're going to basically add to it as we run this loop over the range of m. F underscore WB, that means the function, that means the linear regression function. That's like a shorthanded way of saying that. And remember, the linear regression function is, let me see if I have it here, is this right here. This line right here. So we're gonna basically turn that into code here. So W times X, the first, or not the first, but like whatever the current index is in this loop, that we're gonna call that index from this X array. And then we're gonna add the bias to it. That is the regression. This is gonna create our regression line it's gonna create a point along our regression line rather for this specific index. And then this line here is going to basically add this is going to add the squared error cost of our regression that we just did, the regression line we just made. It's going to add that to our cost here, and then it's going to square it. So I'm gonna come back and write some comments in this. That always helps me. We're gonna use the y at the same index that the x is at, so it matches up with the pair. That's what we want. Let me add some comments here really quick. So, I think I said it incorrectly. This is not creating a regression line. What this is, regression line is created a slightly different way. What this is doing here, this is actually running our model under the assumption of a specific weight and a bias, and it's going to use some index of x. So this is actually running the model with respect to weight and bias for an index of x. I'm gonna do it like that. And then this here is going to add the squared error cost for the so every time this line right here, this okay, so this first part here, this is a prediction and this is a target. So it's matching this prediction for an index of I to a target of index of I. It's going to take the difference, it's going to square that. Cost function, it does this difference in squaring as an iterative like loop along the entirety of our data set. So I'm going to show you here in the notes. I'm going to show you here in the show notes. So this is what it's doing here. So this is saying like take the prediction minus the target and square it. So that's what we're doing here. Prediction minus target, and we're going to square that. So prediction minus the target I'm gonna wrap this in parentheses. I'm trying to figure out like, what's the best way to communicate this in like plain English. Squared, and then we're gonna add that to the cost. Add to cost. Does that make sense? Hopefully. I don't know, you tell me. Okay, so that's what we're doing. We're keeping track of the total. And the reason why we're doing this is because, remember, this cost here, this cost is representing our summation. This cost is representing the summation. This m represents the maximum. Here it's m minus 1, but it could also be m. M minus 1 is just because Python is a zero index language, but you could also see this as like just m. I is the starting index. This could also be 0 if this is like Python, but just remember there's like a little bit of a difference between how indexes are numbered between programming and math. So, but what this cost is, this cost means that for this loop is a summation, which means that it goes from an index to the maximum. It goes from the minimum range to the maximum of the range. And for each of those iterations, it's going to do the difference between the prediction and the target. It's going to square that. And then the next part of that is we're going to do a calculation after this loop is completed, where we're going to create a new variable called total cost. So total cost is going to be the entirety of this summation. And then we're going to divide that by 2m. So to do division, you multiply by a fraction. And then at the end of this function, we're going to return total costs. So I'm going to just add some comments here. So total cost is the cost by 2m. Okay. I think it's funny how my face disappears when I drink my coffee. I'm going to eventually figure out how to get my Ready Player Me avatar thing set up here. That's one of my goals, is to do that at some point. So I won't be putting my face on here for long. Okay, I'm just gonna fix the tabbing there. I need to figure out, is there a way, I don't know if anyone's watching this stream, but if you know a way where I can have like a better coding environment inside of Jupyter Notebook, like that has like more of the, I don't know, like the auto completion stuff that I'm used to in my IDE, that would be so awesome. Okay, anyways, okay, so the next step here, okay, I'm gonna add some notes here about gradient descent, because these are gonna end, this whole thing is gonna end up being on my Substack, so I'm gonna add some notes here, just so when people look at this, they won't get lost. Okay, so the linear regression function, I'm gonna add that. Take this regression model. I'm actually really excited to put this stuff on Substack. Okay, I was gonna put it on my blog actually, but I think Substack is just much better because then I don't have to like futz around with it too much. This is a formula I need right here actually. So I'm gonna grab this. If you're not familiar, this stuff here, this like syntax, is called LaTeX, and it is made for mathematical notation. Let me change this to Markdown. It's made for mathematical notation, so like you can get all those like weird math symbols and stuff. Get those math symbols pop in. Okay. Should I make this a bulleted list? I'll make it a bulleted list. Okay, so in linear regression, you utilize input training data to fit the parameters W, WB. So by minimizing a measure of the error between our prediction, the goal is to error between the predictions. Prediction is this part of our formula. Did that render right? Okay, so between this part of our formula, you may not need those parentheses, and the actual data. Actual data means the data that was the data for the index that was trained. So this is a comparison between what we're deriving from running our model against X at a specific index, and then the actual data is the trained data that is for that index. So what we're doing with squared error cost function and gradient descent is we're using the same data. We're just comparing whether or not the points, these specific points along the regression line, match up. These specific points along the x-axis of the linear regression line match up with the the points along the x-axis of the actual data. And there will be, I think there should be a visualization of what that means at some point later in this. Yeah, there will be. I'm looking right now. Okay, yeah, there will be some great little visualizations. It's actually a very visual one, so I love the visual stuff. So actual data is going to be y index I. Ooh, I did that wrong. Yeah, there we go. Okay, so this measure is called the cost. Let me come in, indent that. This measure is called the cost. Another way to represent cost is, oh, there's so much math notation. You know what? I'm just going to do this by hand. I don't need to copy and paste. Cost is J under, this is a subtext, so underscore W comma B. Or no, this underscore is just WB. There we go. So what this JWB means, this is just a shorthand way of referencing the cost. And the cost is the value that you get from doing this looping thing here, the squared error cost. It's the entirety of this calculation. And the error is the value you get from doing this for a specific index. That, or well, actually not even that, it's just this here. So this prediction minus the target, this is an error, and then the cost is when you do that and add it to do the summation over all of it. But that's like the total thing. Okay, so in training, you measure the cost over all the training examples. Yeah, I'm gonna add that here too. That would be helpful. For cost function, you measure the cost over all the training examples, which are denoted by X. I X in index and Y in index. Okay, so the formula for squared error cost function is in here. I'm gonna go ahead and copy this as well. This is basically what our code that we just wrote is doing. I'm gonna make these large, actually. I like them to be large. I think it'll help for screen visibility as well. Oh, that's too large. Too large, too much. Too much, too much. Oh, I got it outside of here. And let's see. Like that. Bring this down. And this one here as well. And let me go ahead and make these centered. As you can see, I'm very, very tedious with my note taking. Please don't be like me. I mean, I think it helps, but I think it's also a little bit unnecessary to be quite as intense as I am. I just find a sense of comfort in doing this because I tend to think that when I write notes, they're not just for the learning part, they're also for like cheat sheets for myself, because there have been a lot of situations where I've had to come back to my notes as a software engineer and utilize them to remember something, because there's so many algorithms and formulas that trying to memorize everything and hold it all in your head is just a lot. Okay, so gradient descent. How do we describe gradient descent? So formula for performing gradient descent. Formula for performing gradient descent, I have that here. There's actually two formulas, and these two formulas are going to be utilizing the derivatives of weight and bias independently. And I'll explain what that means here in a second. We're going to repeat these two functions until they converge, basically. Okay. So this here is what we're doing. And this is a bit of a shorthand because this right here represents one or each of these here, we're doing them separately for the weight and the bias. These represent summation, or these are like specific iterations of a summation that is divided by our maximum times alpha, and that's subtracted from whatever the previous weight is. So It'll make more sense as we kind of get into it, but in order to make this a little bit easier to understand, I think what I might do, how do I communicate this? In plain English. So we're gonna call this the partial. This is a partial derivative, is what this is. I'm definitely gonna take a break at some point, like a little quick break. If I get to the hour mark, I'll do that. Right now I'm at 35 minutes. I'll definitely probably get to, this is probably gonna be like an hour and a half, 2 hour stream. We'll try and make it as quick as possible. J, or actually I might as well just go ahead and copy this whole thing here. Okay, so partial derivative for the cost function of J for the weight, and then there's going to be the partial derivative of the cost function of J for the bias. And so here where it says J, the cost function for weight and bias, remember that this is like a shorthand. So you can see here, there's this, and then there's this, which means that this J parentheses WB is really shorthand for this here. Now there's a reason why in this note here, there's a reason why it's 1 over m instead of being 1 over 2m, and that has to do with like the first derivative, which is not something that I'm prepared to explain here. But I guess based on like what the course says, all you need to know is these functions here. You don't need to know how to manually get the derivative, I guess is what I'm saying. So I'm going to put the expanded form of this formula in here as well. Make sure that renders correctly. And I don't need this to render large either. And I'm actually put this on another line as well. Does that look good? I think that's fine. And yeah. See, this is the reason why there should be like formatting tools for this, because this can be rather tedious. I don't blame anyone for not wanting to take notes when it comes to this stuff, to be honest, because it can be rather tedious, which is why I'm going to put my notes in Substack. So if you want these notes for your own edification or for your own cheaterliness, just stay tuned, subscribe, follow, and I will have a link to my Substack as soon as possible so you can get all of that. Bing bong. Okay. Oops. Bam. Bam. Take out that bracket. Oh, something's off. Something's off. Now, why is that? There you go. Okay, so I could probably even get rid of this bullet here. Don't think I need that. A tab is is 2 spaces. That's how I'm controlling this here. Cool. Okay, so repeat until convergence. Ooh. And then the other thing to know is when these two are being run, the most important thing to remember is that these need to be updated simultaneously. So here, this equal sign represents assignment, not equality, if that makes any sense. So I guess I could add that here in my notes too. I'm just gonna add here these comments that I added in here. And the above formulas represents equality, or it represents assignment, not equality. Ah, okay. I'm gonna put a little star there because I feel like that's really important, or like an exclamation point. There you go. Okay, so that looks beautiful. Beautiful. I feel like Carmen from South Park would say, "That looks beautiful." That's how he would say it. It's so beautiful. Okay. Love that show. Okay, so we're gonna go through these comments, I guess, and just read out loud for myself, for my own understanding. In the above formulas, the equal sign represents assignment, not equality. So here and here, boom bop, and here and here. And this formula and this formula are the same thing. We just have this as a shorthand, and then this as the expanded form. This J, WB, it's the cost, the squared cost function. And this, it looks like a D and a W. This just means the derivative of W. The derivative of the derivative of this cost function for the weight. And this is the derivative here. This is derivative of the cost function for the bias. Should I make this a little larger? Does that help? Yeah. And up here, I have in my notes here. I'm gonna probably explain this a little bit, but I have here just like a little walkthrough. How do we get from this here, this little shorthand, to our actual formula for the derivative? These are the steps here for doing that partial derivative. But I'm not going to explain that in this video because I don't think I understand it well enough to do that any sort of justice right now. Sorry. Okay, so the weight and the bias are updated simultaneously. I got that in my notes here. This is the gradient. Okay, I guess I could explain what simultaneity means in this context. So, calculate the partial derivatives for the parameters. For both the parameters before updating the variables of WB. Yeah, okay. Okay, now we've done that. Now we can kind of move towards actually implementing. Okay, it says here, implement gradient descent. You'll implement gradient descent algorithm for one feature. You will need 3 functions: compute gradient, compute cost, gradient descent. So this is compute cost, compute gradient, and then compute or gradient descent. Okay. For one feature. Remember, the feature is a specific index within our data set. So first function is compute underscore gradient, and that implements the gradient functions which are merging or converging, which aim to converge. Implement convergence. What that means is that it approaches the lowest cost. That's the convergence. Is when it. So if you think about like there being a parabola or a soup bowl that defines the visuals for your squared error cost, convergence means that it's reaching the lowest point whenever you're changing the weight and the bias using this formula. The second function is compute cost. Ooh. Excuse me. Okay. Compute cost is Okay, so squared error cost function is the squared error cost function over the range of m for x. And that's what we did up here. So we're taking the length of our data set and we're looping over each index. We're running the model against it, and then we're also calculating the cost of that model in comparison to the target. And then we're going to divide that by 2m, and then we're going to add that to the total cost, and then the total cost is what gets returned. So returns total cost. And then the third function is gradient descent. Gradient descent is such a cool word, by the way. And this is this utilizes compute gradient. So basically this function is what's going to call or initialize those other two functions that we had. I guess there's some comments here. How do I? Partial derivative is denoted in Python such as which I'm actually just going to copy this here. There's multiple ways to write the derivative in math notation. So if you see this a slightly different way when you're like out on the internet looking for it, don't be too worried. I'm going to do it the way that I have it in my notes so that there's consistency, but this is not necessarily the same notation that's used in this course. Oops. Did that render? That did not render correctly. What did I do wrong? Okay. What you might see if you're looking at this in another place, you might see it written like, I'm just going to bring this over so you can see it. So if you were to see this somewhere else, you'll probably see it written like this instead of having the derivative and the costs like separated like I have in my example here. So it's like what I have in my example here is like derivative, cost function, and what the lab has here is they've just put them together, but it means the same thing. I kind of like having them separate. It's just easier on my eyes. So the partial derivative is denoted in Python such as, and this needs to be capitalized. Oops. Okay. The author of this is also saying that they use an abbreviation to, they use an abbreviation for shorthand for the term with respect to. With respect to, it's like an assumed meaning or assumed thing in math. What this means when you hear like with respect to, for example here, actually let me get a bigger example. Do it over here. So like if you see here, it says this is the derivative, and then it has this w, and then it has a cost function. The way you might say this in plain English is the derivative of the cost function with respect to the weight. And when you're doing your derivative, the with respect to part is just whatever this is down here. So weight, and then this is bias. And the way that, I guess in this course that they're gonna describe that is they're just using WRT as just like as a acronym. I am kind of anti-acronym. I don't know if that's like language fascism or not, but I don't really like acronyms, but I'm going to go ahead and put it in here in case you're taking their course so that there is some consistency. I don't want you to be lost, but I am not going to use this. Actually, I'm not even going to put that in here. I'm not even going to put that in my notes. I'm just going to leave it out. I'm just going to ignore that. Okay. So what I'm going to do is I'm going to take a little break here for like 5-10ish. It's 5 minutes to the hour, so I'll be back in like 5 minutes-ish. I'm going to leave you with some good old music. Just enjoy, or you can skip forward. And then when we come back, I'm gonna do the computation for the gradient. I'm gonna walk you through that. Then we're gonna make some visualizations that show how the gradient looks and how the gradient is working. It's gonna basically break down for you the steps the gradient is taking as it approaches the local minima or the local minimum. Then we're also going to walk through the gradient descent as well. The gradient descent is like the actual iterative process of going through the steps of that gradient. And then after that, let's see. Yeah, we got some plotting stuff coming up here too. So yeah, stick around. Like I said, I'll be back in like 5-ish. Probably like 5 minutes, give or take 5 minutes. So let's just say 10. let's just have a crazy time and say 10. Okay, so I won't be too long. Thanks for checking out the stream. Don't forget to check out the links below if you want to know more about the work I do. My link tree is the best place to start. If you want to get some of these notes as they're made instead of waiting for the Substack, I'll post them on my LinkedIn. All the notes on my Substack are going to be available for free on my LinkedIn. You don't actually have to pay for the Substack. The Substack is just going to be there to make it convenient and put everything in a centralized location. And this is literally my class notes from taking this course. So check that out. Okay, I'll be back. Don't worry. I'll catch you in a bit. Hey everyone. Okay, I'm back. Sorry that took a little bit longer than I thought. I don't even know if anyone's watching this. Anyways, I did get some coffee. I had a little stretch, and I think we're ready to go. So let's just jump back into this. Hey, it's nice to see you again. Okay, so where we left off is we were just looking at the two operations, the two gradient operations with respect to the weight and then with respect to the bias. And then now what we're going to do is implement this in code. And then this code that we're going to write next is going to attempt, at least, to return the derivatives for these two gradients, or for the two cost functions for these two. Blah, blah, blah. It's going to return. What we're going to do next is going to return this part of the formula and this part of the formula. So the derivative of the cost function with regards to the weight and the derivative of the cost function in regards to the bias. That's what I meant to say. Okay. It's a mouthful. Saying math things like out loud verbally, it is kind of awkward. Okay. So, our function that we're about to write here is compute gradient. It's going to compute the gradient functions which aim to converge. And I guess we could write in our notes here. This is going to return okay, so where's that derivative part start? This here. Oh, mark down. derivative for the cost function with regards to weight. And remember, this is the squared error cost function. And the second one is going to be the bias. Okay, so yeah, let's go ahead and do the code for this. So we're going to define our function. Arguments. Add some comments in here. Compute the gradient regression. So our arguments. Oops. So x. This ND array, I think this is just like showing us that we're using a specific. So we're using this NumPy thing here, and when we create our array using NumPy, this is actually creating a multi-dimensional array, but we're only using the first dimension. So this here is just showing us here that it's just showing us the dimensionality, I think, is what that's supposed to represent. Because when you call like the length here, we're just this 0 here that correlates to this. So there could be other things and there could be other dimensions in this array, but we're only using the 0th one. Okay. So this is the data, and then there's m examples, an array of input data. M examples. And then similarly, we have Y. Your Y training data and your X training data are always going to be the same length. So M, the length, is going to be the same. We just use the X to represent the length, but it goes for both. So array of target values M are which correlate to X. WB. The course calls this a scalar, which I understand why, because scalar is just a set of two values. In physics, that's like the magnitude and the direction, but it's just two values. It's like an array of two values. But I don't know why they call it a scalar, because in this context, they're not paired, except for in the sense that we know these are like the actual coefficients. So, but like in the code part, we're not treating them as pairs like we would in like a set or anything necessarily. I have to figure out why they call it that way, because that does seem a little bit weird to me. Okay, so these are the model parameters, and then as we already said, this function returns something. In this case, it's going to return the derivative of. It's going to return this derivative of our cost function with regards to the weight. So here, or the gradient rather. Okay, so that's probably something to note. When we do this notation here, we're actually talking about the gradient. Make sure I didn't get that weird. I'm gonna fix that in my notes here so it's like consistent. this to B. So the partial derivative of a cost function with regards to the weight is the same thing as the gradient. So the derivative of the cost function is the gradient of the cost. The derivative of the cost function is the gradient to the cost. For that parameter. Okay. Cool. Cool beans. Cool beans. Okay, so now that we have our notes there, we can actually write our code here to do this stuff. So remember train samples. Remember M is the size of our m.shape. 0 is the actual size of our data set. I'm going to start both of these at 0. I'm going to write this out and then I'm going to come back and try to talk through it because this is very abstract, so I might need to just focus a little bit here. Sorry. Actually, I think I can handle it. Okay, so it looks like this here. This is us for index, or for x at index. Run the model. I'm just gonna say linear regression model for x index. So this whole loop is going to be going over this following code for each index. So we're delineating this gradient cost because this is for a specific index, not the entire thing. And then this is the get my language right here. I am such a stickler for like language. Makes me a little slow at doing this. Okay. Okay, so the output minus the target derivative for an index. I'm just going to call this the gradient cost for an index. And actually, I'm just going to put it here because I'm going to do this twice. Okay, let me go look at the formulas again real quick. So the difference between these two formulas is that the weight is going to be multiplied by x at whatever the index is. Just a sidebar, even though it says x at the index here, it's really 2x at the index, but it gets reduced to x at the index because originally this is 1 over 2m. So the 2 here and the 2m, they cancel out the 2's because you multiply a number by itself, or you multiply a number by 1 over that number, it cancels out. That's like algebra. So it ends up just being x, but it's really 2x at the index, and this is really 1 over 2m. So okay, so this here is what's happening here. I don't know why. I can't explain to you exactly why the derivative formulas for the weight and the bias are different, but they are. And the big thing to know is that this x at the index being multiplied by this, it only happens for the weight. It doesn't happen for the bias. Okay, so, and then we have our placeholders here. So we're just going to add these values to the placeholders. Let me put some good spacing in here too. What's that? What's like the name for when you do like, what's the name for that called? Plus equals. Oh, it's the add and assign. Add and assign index derivatives to total, and that's going to be like that. So it's saying that this derivative, or this gradient cost with regards to the parameter w, or the weight, it's going to have this indexed value added to it. And this will be, so I'm going to add a comment here. So this is the gradient cost for the entire training set. Gradient costs for the entire training set. Okay, we're going to take this, we're going to do the same thing with the bias. And I think that's right. With all these like W's and B's, I'm getting very much Saturday morning cartoon on the WB channel. Getting very much like arcane wizard language. I think I might have said earlier that acronyms, they really be my weakness. I'd be struggling. Anyways, okay, so now that we have these totals here are basically summations, similar to what we did before when we were computing the cost. This loop here is just a programmatic way of doing summation. We're going to take the sum, so the sum gradient cost of the entire training set. I'm calling it cost because there's two of them. And what we're going to do next is we're going to divide the sum gradient cost by 1 over m. We're just going to say multiply the sum gradient cost by 1 over m and DQ, Dairy Queen. Okay. Speaking of which, this video is sponsored by the no, just kidding. Dairy Queen. Lies. Okay. Divide by m, and then same thing for the derivative of, or for the gradient cost of the bias. If it was up to me, I would not do the the variable naming like this. Not if I was teaching it. Like, as someone who's like trying to learn the field, I suppose, like, you have to just do what the field says or the standards are, but I don't think I would do the naming conventions like this. I think that the best way to do it cleanly is to make it a little bit more intelligible. And sometimes, like, when people are looking at stuff like this, they may not know that this D, J, and DW is like coming from math. I suppose if you're doing this stuff, you might know that, but I like having language that more reflects the way that I personally am summarizing things in my head. It's just personal preference. Okay, so we're returning, this return is apparently returning two things. I didn't know you could do that in Python. I need to learn more about that. Okay, so nothing to run here quite yet. We're just setting up this, and this is going to be used by this gradient descent function that we have coming up here. I'm just going to double check. Okay, so these are our, I'm just going to walk through this here. Okay, so compute gradient, typo, takes in 4 parameters, or 4 arguments, the X training, Y training, weight, bias. First thing we do is we set up the variable to hold the size of our training examples, which is a number that represents the length of X train rather. X train is, X is this basically. And then we set up placeholders for the gradient costs of the entire training set, separately for the weight and the bias. And these two need to be updated simultaneously, which is happening here. The reason why you update them simultaneously is because if you don't, then if you were to, for example, do this here, this iteration, and then update your derivative with regards to the weight, and then perform your derivative with regards to the bias, the derivative with regards to the bias utilizes the weight, and so that it's going to just keep changing, and it's going to, it's like another, it's a whole nother function that you're doing at that point. So they need to be updated simultaneously. I think I might actually have some notes here. I need to refresh my mind on that exactly. Did I have it in here? Yeah, I guess this is here. So this temporary weight, this is what we have here for so these are, the temporary weight is basically these two here. When they're added to these placeholders, I guess. Now, actually, this is like slightly different. This is a slightly different approach than what we're doing in our code, actually. So I don't think this is like an exact in code. And the way you do it with code, I remember the lecturer said that the way that this is done with code makes it really difficult to actually do it the incorrect way. He did say that, but in the example he was giving, I guess they did it this way to explain what would happen if we did it incorrectly, which you would have to go out of your way to do incorrectly with the code, the programmatic way of doing this. But you can see here that the weights and the bias, when you're doing this, they're going to be constantly updated in proportion to your alpha value. And your alpha value is going to, so it's going to be changing that number. And what happens is if you don't update them simultaneously, then they're not going to update together, and it could give you like the wrong result, and that result will become increasingly wrong as the algorithm runs. That's what I understand, at least. So we'll be able to actually look at that here. But in this case with my code here, I think it wouldn't, this doesn't really have to be a problem, so I don't think we'll have an issue. Okay, so it says here, the lectures describe how gradient descent utilizes the partial derivative of the cost with respect to a parameter at a point to update that parameter. Let's use our compute gradient function to find and plot some partial derivatives of our cost function relative to one of the parameters, the weight. So every time these run, we're getting a weight and a bias that is delineated by some subtext. That's like, it's like a numerical subtext. So weight with the subtext 0 is the first time this loop runs for that index. It's always going to match the loop, I suppose. Yeah. Okay, I'm just going to go ahead and run that code here. This is utilizing some stuff that is in a package that's provided by this course. I mentioned at the beginning of this video, it's this Lab Utils Uni, so this is not something I wrote. But basically what we're doing is we're running, we're going to be using the data set that we created at the beginning with those costs in relationship to square footage. We're going to pass in the compute cost function, and we're going to pass in the compute gradient function as well, and then we're going to show our thing here. Oh, I think I might need to update my file to let me I guess I need to update my file. 1 second. Okay. I'm just going to copy this into here, and I think this will, no, did I type that wrong? Oh, it should be an S. I just had a typo, so that was a wasted step. Just ignore me. I'm just over here tripping out. Okay. This is like the dialogue that goes through my head when I'm like programming, by the way. I have to talk to myself. Okay. Yeah, I just had a typo. Okay. Okay, so one thing too, I guess since we had our VS Code here, I can show you what this is doing. It'll help me to look at that as well. This PLT underscore gradient, something that would not be easily gleaned from this code is like, how are we establishing the weight and the bias? Like, this is just function. There's nothing happening here that would suggest why we're getting these numbers here. Well, with their provided code, they're giving us fixed values for the bias, and it looks like here too. I think this is an interactable thing. Is this interactable? No, it's not. Array. Okay. Yeah, they're giving us a fixed bias. So the bias is not going to change, but they're giving us 3 different values for the weight. And that's what's depicted in this here. So this is basically what happens. And what this diagram here is illustrating is like what it looks like to do a gradient descent only in the sense of performing this for the weight, which is why we're seeing a parabola instead of a soup bowl. If you remember in the previous video, I was showing that there's 2 ways. When you're only doing the function of W, of the weight, you can see this in a parabola. It's very simple. Or if you're only doing the bias, I guess it'd be the same as well. If you're doing the bias and the weight that are not fixed, then you would have this 3D surface plot, or you can do a contour plot as well. So here, we're only seeing this parabola because for this time being, we're only concerned with the gradient descent of our, with respects to our weight, I guess. Yeah. Okay, so the gradient descent, what it's doing is it's just moving down. You initialize it with the starting point, and then the derivative that you're getting from doing this here, this is the one for the weight. The derivative, like if you were looking at a derivative on a chart, on a plot, a derivative is just a slope. It's going to give you like a tangent along a curve is what that is. And it can be positive or negative. This is a negative, this is positive. There's some other stuff going on here that we're going to do next, but this is just like their little example, I guess. Because the actual gradient descent involves another value called the alpha that we haven't even gotten to yet. So that's not represented in our code yet. Okay, so the gradient descent for this is trying to get to 0. With our data set here, when you only have 2 columns for your data set, or 2 rows rather for your data set, you can always have a cost minimum of 0. Sometimes you can't though. I don't know what a quiver plot is. Our bias is fixed at 100. So here. Okay. We got some more notes here. This is going to be a very long stream. I might need to break this up, to be honest, because there's quite a bit left here. I might do that. I don't think I'm going to do the entirety of this lab. I'm just going to go for probably another 10 or 15 minutes, and then I'm going to call it, because this is quite a bit of info. And we still have to do the gradient descent, and then we have to actually initialize our parameters and play with them outside of what's fixed. So yeah, I'll tell you what, I'm gonna finish up this section, write some comments down here, and then we're gonna call it. I don't wanna keep you too long, so. Okay, so it says here above, the left plot shows the derivative of the gradient, or how do I say that in plain English? The derivative for the squared error cost function with regards to the weight. I'm gonna copy this. Okay, so and remember, the derivative is the slope, the tangent. It's a tangent, which is a slope. A slope along a curve is always going to create a tangent when you're talking about it in terms of derivatives. Slope of the cost curve related to oops. Yeah, I'm definitely getting tired here. Related to the weight at various points. So the left plot shows the derivative of the squared error cost function with regards to the weight is what this means. Let me just say that out loud 10 times. So the derivative of the squared cost function with regards to the weight and it shows it for 3 different points, and all 3 of these are slopes. This squared error cost function is so the reason why this is a parabola is because whenever the squared error cost function is running, it's like squaring it, of course, and it's dividing it by 2m. So that means that if you were to plot out those points, it'll always be like this parabola if it's only for one parameter, and if it's for 2, it'll be this like soup bowl shape. So, as I mentioned, the slope, or actually, depending on the weight, the slope can be either positive or negative. And the derivatives will always lead gradient descent toward the bottom where the gradient is 0. The derivatives, how do I say that in my own words? Derivatives will always attempt to converge at the lowest cost, which is the minimum. So it'll always try to descent. That is what the descent is. Okay, so for this example, maybe what I should do is just note here, in this example, our bias is fixed at 100. What are the values that we're using for? I don't understand what this means, though. This seems like it's overriding itself. That is a little weird to me. W underscore array or np dot line space or lin space. What is that? Oh, okay, I know what that's doing. So here where it says np.lin space, this is saying that we have a range that will go from negative 100 to 500, I guess. None of this seem right. Wait. So this 50 is the interval from negative 100 to 500 in increments of 50. But this is going to 600. I don't know why. Yeah, there's some nuance there I don't think I'm getting. And then this one here is the same thing, from 0 to 400. So here, in increments of 50 as well. That's what that is. I don't know why these two have the same exact name and how it's, yeah, that's a little weird to me. I'm not sure how that having the same name for a variable in Python works. I guess what I could do is I could just play around with this for a second. I like to do this, don't mind me. Well, it is doing what I thought it would do, which is overriding the value. I don't know why they're doing both. Maybe I'll just chalk it up to some issue. Maybe, I don't know. This doesn't seem like this is doing what this doesn't make sense here. But you know, people do make errors. I don't want to be too quick to call it an error, but this is certainly not treating these as separate. So I don't know. Should I like send a note or something to them and ask? I could post in the forums. There is a forum that relates to this course, by the way. I don't think I have a link to it right now. I won't bother. But yeah, that is weird. Okay, so back to this. The quiver plot on the right side now. Let's break into that and see what that's doing. Okay. Do my little things here. Actually, I don't like that one. There you go. I love to put emojis in my notes, by the way, if you can't tell. I've done that a couple times here. I usually do it a lot more, especially when I'm at work. I find they just help with my visual acuity. I'm gonna make this bold. I want to make it easy for my eyes to go exactly where they need to. Okay, so for the quiver plot on the right side here, this here, the quiver plot on the right side provides a means of viewing the gradient of both parameters, meaning the weight and the bias. The arrow sizes reflect the magnitude of the gradient at that point. Oh, okay. What that means is like, as the gradient function runs, the gradient becomes smaller based on how do you do it? Alpha. Based on alpha. Alpha is something we haven't gotten to yet, so this is probably not going to make sense if you're just watching this part of the video. Don't worry, I'm going to come back and that's going to be in the second version of this study session. So as the gradient function runs, there's this value, there's this thing called alpha, and the alpha is what you're subtracting every time you run your gradient descent. And these arrows, the size of the arrows represent how big or how small rather this gradient is as it proceeds along this descent. And by the time you get to like the minimum, that alpha and the function itself ceases to make any difference from iteration to iteration. That's how you know it's done, is when it doesn't do anything after a certain point. So the direction and the slope of the arrow reflects the ratio of the derivative represents the ratio of the derivative with respect to y and the derivative of, or with respect to the b, between the bias and the weight. Okay. is the ratio between excuse me. My yawns show up weird on this like little face thing I got going on here. Okay, so the direction of the slope is the direction and the slope of the arrow is, or they say reflects. The ratio between the derivative of the cost function with regards to the weight and the derivative of the cost function with regards to the bias at the respective point. The gradient points away from the minimum. The last note here is it says the scaled gradient is subtracted from the current value of the weight and bias. What that means is, so here, these are our two operations that we're performing in our loop as we get these gradients. And I mentioned that there's this alpha. This alpha is like some number that you have to choose, something for. But in the, in this full function here, this full equation, this weight, every time we run it, is going to be reassigned to itself. And the previous value of it is going to have the current derivative of the cost function with regards to either the weight or the bias subtracted from it. But that it'll be multiplied by our alpha value. That's just to say that this weight, as it iterates, it's always going to become smaller and smaller and smaller, which is why in this quiver plot here, these arrows are going to become smaller and smaller and smaller as they move towards the minimum, but they're pointing away from the minimum. And the direction they're pointing in is either a negative or positive direction, which is a way to visualize the slope or this tangent along the curve. But this diagram is different because this is with regards to both the bias and the weight in one visualization, whereas this one here is just in regards to the weight. So this is similar to looking at a plot. Can I make that easy to see? So this is kind of similar to the plot here, I suppose. That's kind of what this is. Except instead of these concentric ovals or whatever you might call these, these are just like arrows, because these arrows have the capacity to indicate direction. the direction and the size. So that means it's a vector. I had my terms mixed up when I said scalar here. These are scalars. Scalars are a single value for magnitude. Earlier I think I said I was calling this a vector and getting confused. But this is showing us vectors. There's probably something in their code here. Yeah, the code for me right now is a little bit intelligible. My brain is kind of tired right now, but basically what I'm saying is, like, whenever you see this arrow and then the size, that means that it's a vector, and it's representing, each of these points is representing a vector, and that vector is consisting of a derivative for the cost function with regards to b, and derivative for the cost function with regards to for the weight. Something like that. I might have to go back and look a little bit more into that. I feel like this diagram here is useful, but I'm just not familiar enough to have an intuitive relationship with it, so that's okay. It's okay for now. The scale gradient subtracted from the current value of what? So gradient points away from the minimum. Okay. I think we're at a good ending point for this part of the gradient descent. I'm gonna come back to this. So I guess this will be another 3-part little section of our series here, because I'm gonna come back and I'm gonna finish this lab. And then after that, I'll do a review that will go through the entire lab, which will be more for tutorial purposes. So for right now, we're just focusing on the study portion. As I mentioned before, if you go check the links down below, you'll be able to find me on like LinkedIn, Instagram, all that jazz. And you'll also be able to find a link to the course that this is based on. What else? Let's see. I have a tech blog that's not being updated at this exact moment, but I will probably issue these notes on Substack so that you can get them in PDF form. I think that's the best place, and I could probably have that up probably sometime early next week. What else? If you want to know more about gradient descent, like the actual math, especially like this derivative part of this is a partial derivative that we're doing over the cost function. Daniel explains that really well. Great channel. That's where I started when I was like learning about coding in general at the beginning of my journey. So I would check that out. Links in the description. Yeah, so just stay tuned and come back, probably sometime today, and I'll be posting the link in my LinkedIn if you want to watch this live. Otherwise, you can just watch this in hindsight. And with that, I just want to thank you for coming by. I hope you have a great weekend, or whatever day is next for you. I hope it's good. So with that, I bid you adieu. My name is Key Clark. I also go by Mater Dev.